All right, Linux. Go through. Okay. So we finished off last time talking about scheduling in Linux, and we had talked about this briefly before when we were talking about scheduling specifically. We covered a little bit of how Linux works, but one of the major ideas is that we have these two arrays, right? And they have the list of tasks, and we service the tasks in the active array, and as they get kind of run out of credits to be scheduled, they get moved to the expiring array. Once everyone gets moved over to the expiring array, they flip it back over and then can start running through the active again. So the priorities, what kind of different factors come in as far as decisions in servicing a priority? What's the main difference between a priority? How does the operating system treat, or the scheduler treat different priorities differently? How does it treat them? I mean, what does it do? Having a different priority would... Okay, so one thing is it changes how much CPU time it gives you. Overall, or what? Okay, well, I mean, like, for example, in most scheduling, we don't know how many units they'll need, right? They don't ask for X units beforehand, right? So, right, I mean, yeah, I mean, the idea makes sense is you want to give processes how much CPU time you like, and ideally we'd know how much CPU time each process wants, and we can, give them that. But we don't have that kind of information. So these priorities, right? Different tasks, different processes have different priorities. So I'm the scheduler, and I come here and I say, okay, I need to service one of these tasks. What kind of decisions do I make based on their priority? What kind of... Is every process serviced the same way? And every priority serviced the same way? No, so how are they serviced differently? Just, I mean, like, there's at least one very simple, straightforward way they're serviced differently. What does a scheduler do? On the CPU. So, what kind of decisions does it have to make before putting a process on the CPU? Okay, again, we don't know the future, right? As a scheduler, we can't predict, here's how long this process is going to run, or how much it wants, or anything like that, right? Okay, real simply, we can do things like change how big a time quanta, right, to give, how big a time slice to give each process based on priority. So here, we already see that different priorities get different time quanta, right? Based on the priority, also, we decide whether or not we're going to, we make decisions about what priority to put them at next. In the case of Linux's system, the priority determines how much kind of credit you have right? These ideas that every time you're serviced, you kind of remove some of your budget for running, and then eventually you'll spend it all and then not have any. So by changing these budgets, we can say how long overall within one kind of cycle of these, how long overall the process will run on the CPU. By changing the quantum, right, we change how long a process will run in one slice, right, in one turn on the CPU. Okay? So these priorities can affect that. What is the purpose of this system in Linux where we go through this active array and allocate time for all of these processes? What's the purpose of moving to this expired array and then flipping them back so that we can have a new active queue? What is the purpose of this mechanism of going through the active array until they're all moved into the expire array and then coming back? What benefit is there to that? What's that? Right. That's exactly the reason. You prevent starvation. So what is starvation? Right. And how could that potentially happen in a different scheduler? Right. So like if we have like a very rudimentary priority system where a higher priority thread a higher priority process will always be serviced before a lower priority one. Well, if you keep having higher priority threads or processes, there's a potential that you'd never service a lower priority process. So this mechanism of moving it over, right, you'll eventually empty out the active array so that there's nothing else that you can service for that lower priority before that lower priority thread, right? So this type of mechanism is a technique for preventing starvation, right? Starvation is obviously a very important problem for a lower priority process, right? If you're never going to get CPU time, you'll never execute any of your instructions. Okay, so that's the basic idea behind the schedule, and again, we've seen that in the chapter on scheduling, and we also saw some other types of scheduling. We saw some we saw some different techniques for having prioritized queues, where we set up some rules, like in Solaris, for what would make you migrate to a different priority, right? Based on whether you expired on your own or you gave up the CPU voluntarily, that kind of thing. So this is Linux-specific style that we just saw, and we'll also take a brief look when we get into Windows how it does scheduling, and it does it in a very different way. Okay. Kernel synchronization. Okay. Synchronization is all surrounding, what we saw with synchronization in the general synchronization chapter, where it's a way of coordinating multiple processes, and it involves things like interrupts and locks. Okay. Inside the kernel, we have a bunch of different kind of processes or threads of execution or sets of instructions that will want to run, and this will change over time. One of the most straightforward ones are one of the most straightforward is when a user process or a program in general just asks the kernel that it wants to run something, right? It says, I want to use a kernel function, like accessing a device, right? Or, like getting information from a disk, that kind of thing, okay? So that's one way that we run more of the kernel code, right? And then it can also happen implicitly when we do things like interrupts. And one of the examples they give here is when a page fault occurs, right? When a page fault occurs, what is that involved with? What are page faults? Where do we have page faults? memory, right? When we're doing memory management, okay? So page faults occur when we need to load a page of memory, a page from a program into a frame in memory, right? So we've seen in the memory management chapter that there's a lot of different decisions that have to be made and a lot of different actions that need to be taken when you have a page fault. When you go to access a particular area in your program's memory and it's not in a frame. Well, we can't operate on that with the CPU, right? So we need to get it loaded in. So we make decisions on what frame to replace, finding that page on disk if it's on disk, copying it in, and tracking various pieces of information about that frame or that page. Okay? So all of these instructions for what to do when a page fault occurs are part of the kernel, and this is another way that we can get kind of some of this kernel code to run. A device driver may deliver a hardware interrupt, right? We've seen hardware interrupts even from the very beginning. Hardware interrupts like I'm done reading information from a disk, right? So I'll interrupt saying that this block is ready, and then we need the kernel to stop what's running and service the interrupt, right? It needs to go and retrieve that block or notify a program that the block is ready, or whatever instructions that we need for that particular type of interrupt. Okay, so all of this type of execution, right? All of these examples that we just went over, right? Is kernel code, right? This is different from our user code that we're running in our programs and our processes that that we're trying to run on the operating system. This is all kind of the housekeeping that a kernel does. Okay, so we have a lot of synchronization problems there because most of the type of code that runs in these examples, right, have what are called critical sections. So what are critical sections? What is a piece of code that has a critical section? What is required for that code to run correctly? Atomicity, right? All of the critical section needs to run uninterrupted. Okay? We talked briefly, in the context of having interrupts, right? That we can quickly lead to some problems if, while we're handling an interrupt, if another interrupt occurs, right? And then if we go to service that and another interrupt occurs, we can get into this kind of recursion where we can't get out. So typically, we need to either, we need to stop interrupts or find some way of preventing other code from running while we're handling this interrupt, right? So the whole idea here is the same type of problem that we saw with things like the producer-consumer problem or any of the synchronization problems where we want to lock out everything while we run a particular piece of code so that nothing gets interrupted, nothing gets used by another process. Okay? So, this kernel synchronization, Linux has mechanisms for preventing other, for servicing these critical sections. Okay? We list here two techniques for protecting critical sections. Okay? This first example, or this first technique, okay, is having kernel code be non-preemptible. Okay? Non-preemptible just means you cannot interrupt it while it's running. Okay? Normally, our processes, as we've seen with scheduling and user-level processes, is all of those instructions are preemptible, right? That's what leads to all of our multitasking and scheduling techniques like round robin, right? Or a lot of the techniques use preemption to stop a section of code running so that we can schedule a new section of code. Well, critical sections in the kernel code we make non-preemptible, right? Which means that we can finish this complete section of code, like servicing an interrupt or any of those other examples we saw, get finished with it, and then serve it. Then we can do whatever we need to service the next one. So they do this through this flagging mechanism. So they have this need underscore rescan flag, right? Which just means that if it's set, just means that we cannot stop currently running code. So this other piece of code that wants to come in will have this flag set so that when we return from the non-preemptible code, we can service all the things that kind of wanted to interrupt that piece of code. Okay. Second technique applies to critical sections that occur in an interrupt service routine. Okay. And this we just basically use the basic hardware turning off interrupts to make sure that a particular processor cannot be interrupted while we are servicing a hardware interrupt on that processor. Okay, this one is more the idea of like hard disk returning or keyboard input, things like that. Okay, but both of these types of techniques are used, and this is kind of a specific instance of what we were talking about in general about what to do when we're using this kind of interrupt code or service of interrupt code. This is specifically how Linux handles it. Okay. This, I don't know if, like I said, this second example is more the hardware interrupting the kernel running code, and then this first one is more the I'm asking software for I'm asking the operating system kernel for a service of some sort. So this is kind of voluntary, I guess, as processes running certain pieces of kernel code, whereas the second one is more external factors coming in and interrupting the processor. Okay, so that's why this one needs to turn off those interrupts before doing anything, whereas this one can use more software-style handling of this additional processes wanting to run. Okay. This first point here, okay, having these design so that we do not have to disable interrupts for long critical sections. In other words, critical sections that will take, just all of a long set of instructions need to be executed without being kind of preempted or interrupted. We give ourselves, we have a particular design here that makes it so that we don't have to disable interrupts during that period. What is the drawback of disabling interrupts? Why would we have a desire to not leave interrupts off for a long period of time? What happens to interrupts that occur when we've disabled interrupts? They're gone. Right? There's nothing to let them wait. Right? There's no code that can run or no service routine that can kind of put them off. So every time we do turn off interrupts, we're making it so that we might miss some interrupts. Okay? But I mean, there are some styles of interrupts that we can go check for once we get back. Like if an interrupt is really just a signal, like for example, if you have a disk and you write to a buffer and then interrupt saying, "Oh, this information's ready," just because we can't catch that interrupt, we still have the data. So there's a potential that we could go look for it when we come back. But the main thing here is that disabling interrupts is a pretty big deal for a processor because you are stopping handling of all of these external factors that really it's your job to handle. Okay, so minimizing the amount of time that we need to disable hardware interrupts is a good thing. Okay, the technique they use is this idea of using a top and bottom half of a service routine. Okay, and what they're saying here is that the top half is what we kind of describe the idea of turning off interrupts. So this is the normal style of let's turn off interrupts and make it so that we don't have to recursively handle interrupts. In other words, get interrupted while we're handling an interrupt, which could then in turn be interrupted. Okay? And then they have a bottom half where interrupts are re-enabled. Okay? And the idea here is to use scheduling and software or kernel code to handle more along the lines of what you said, Lindsay, the idea that if an interrupt occurs, we'll make it wait. So the top half, we can't do anything to make it wait because we can't run code in response to it. But the bottom half, what they're saying is that we kind of handle the interrupts within kernel code so that if an interrupt occurs, we'll receive it, but what we'll immediately do is put it off to to be handled later. Okay? So the idea is that if you design your interrupt service routine, like if you're writing the operating system, you can design your interrupt service routine where you don't have to just say, this whole thing is a critical section, let's turn off interrupts. Okay? You can isolate as much of the code that really needs interrupts turned off into a top half, and then your kind of longer running, maybe more complex code, but doesn't necessarily need interrupts turned off in a bottom half. Okay? So obviously at that point you need to know what kinds of instructions are safe to run in a bottom half and in a top half. Okay? Completed by mechanisms for disabling selected bottom halves while executing normal foreground kernel code. This last bullet, the bottom halves, we have options as far as how we run them, whether they can be rescheduled and things like that, unlike the top halves where interrupts are disabled. So while we may need to run the bottom half kind of as a single block, we don't necessarily have to run it right then and there. So we have options as to when we can run this and what kind of styles we can run and whether other code can run before it and things like that. Okay, so here we see just a chart showing the hierarchy or prioritization of these different types of stopping preemption or protecting different routines. Okay. Notice who's at the bottom, the user mode programs, right? These are the kind of general programs that we run that are not kernel core code. We have kernel system service routines. So we divide these service routines into preemptible and non-preemptible, right? If we can make a service routine preemptible, it makes sense to because we can not having to worry about these critical sections or having code that's safe to pause and continue running. We've seen that this can help out with performance because the more we can preempt, right, the more flexible our scheduling of this code is and whatnot. Okay, and then their kind of unique aspect to Linux is that they've broken up the parts that cannot be preempted into two pieces, bottom half and top half, and top half is the kind of most restrictive protection level where we actually disable hardware interrupts. So notice from all of those different scenarios of how we handle interrupts, how we handle critical sections, we've broken it up into all these sections, and only the top one needs to actually turn off hardware interrupts. So that's the goal of having these different categories. Okay. So scheduling. Okay. This is really just a little bit more information on what we saw with the diagram before of the 2Q system. Okay. A time sharing out. They break up their scheduling algorithm, the actual algorithm that decides what process will run next. Right. They break it up into two pieces: a time sharing algorithm and a real time algorithm. Okay. The time sharing algorithm is kind of the general idea of what we've been talking about when scheduling, right? We want to take a bunch of processes and run them on the CPU in a way that kind of divides up the CPU in a fair manner, maybe with a little bit of adjustment for priority, okay, and how often they are going to input output as opposed to CPU bound. Okay? But they also have a second algorithm which handles real-time tasks where they have absolute priorities. So we saw before in the priority levels that there were kind of two sections, a real-time section and then a normal section. Okay? We haven't talked a lot about the idea of real-time operating systems or real-time operations. Real-time operating systems, I don't really do a whole lot with real-time operating systems or embedded systems. Real-time is, it's not really necessarily about being able to quickly service processes. It's more about the operating system or the scheduler being able to give a process guarantees as to how it's going to be scheduled. I can give guarantees on how often I'll give you a response. In other words, how an upper limit on the response time of scheduling you, how long you'll wait in a queue, right, before you get some CPU time, how long a time you get to run on the CPU before I'll forcibly preempt you, right? So it's not about how quickly you can do that, it's that I can tell you exactly what's going to happen, right, at least to within some sort of range, okay? This is very important for certain operations like real-time operating systems are often used with, like I said, embedded systems where you might be dropping off little computers with sensors on them in Antarctica, right? And you drop them off in there and they have temperature sensors and I don't know, pressure and humidity sensors or whatever on them. Real-time operating systems might be critical for you to gather data using those sensors. In other words, if those sensors are sensitive to, if you don't take a reading within this amount of time, I'll lose the reading, right? So then real-time operating systems can give you guarantees that no matter how much I'm running, no matter how much I'm doing, I can service these sensors or whatever this many times per second. Okay? So that type of scheduling is different from like what we've been seeing in the general scheduling, which isn't real time, right? In our general scheduling, we're kind of doing a lot more guessing as to how long it'll be before I can run something, a process that's waiting to run, right? And then we also are kind of guessing as to how long will I be able to let you run, right? Once you do get the CPU and whether I'll interrupt you or not. No matter how high your priority in a normal scheduler, sometimes I might interrupt you because an interrupt service routine I need to run comes up, or some other operating system kernel code I need to run comes up. So that's why this is kind of split up into two different pieces. The part that we are more familiar with is the first bullet here, which is the time-sharing algorithm. Okay? So a process scheduling class defines which algorithms to apply. So this is an attribute of creating the process. When you create the process, you put it into one of these classes as to whether or not you're going to be scheduled by the typical time-sharing algorithm or you're going to be scheduled by the real-time algorithm. Okay? So the time-sharing algorithm, again, gives this idea of credits to a process. So here we say that the credits equal credits divided by 2 plus the priority. Okay? So this formula that we see here says how many credits you get, and we've seen that as we run in the active queue, the idea was that every time you run, you're charged a certain amount of credits, and then we try to get, once we expend all of these credits by being scheduled, we get moved over to the inactive queue. Okay? And then eventually everyone spends their credits. Okay? By doing this, by using this credit system and the priorities, this is Linux's way of guessing whether or not, or determining whether or not you're I/O bound versus CPU bound. Because again, in all of our scheduling, we saw that that is kind of one of the main things that you can do to increase your performance in scheduling is putting all of the I/O bound processes into short time quanta that you service very quickly, and then all of the CPU bound jobs into things that you kind of schedule a little bit later, but you let them run for larger chunks of time. Okay? Oh, and then this slide is talking about the real-time scheduling, okay, again, which we didn't really go into too much depth because we didn't really cover real-time specifically. FIFO and round robin, these are the same algorithms that we saw in the scheduling tab, right? First in, first out is just line, and then round robin is going through the list and servicing each. Again, with real time, we're more concerned with the priority of the process than we are in fairly scheduling everyone, because we need to be able to make guarantees to each of the processes. And one of the big things is that in real time, typically, if you can't make a guarantee, you don't schedule them, right? If I can't give you a guarantee of how long you'll run or how long it will be till you run next, I stop you. I don't try to do my best effort of scheduling. Okay? So that's why these are really separated into two different classes, because the goals of each of these scheduling is very different. But having these two classes and being able to schedule both types is, makes Linux very flexible. And we see this in how Linux is used. It's actually used in a number of different scenarios. Everything from, servers sitting in a, enterprise server room, all the way down to running on like Motorola phones, right? So all of these different ways of using it are because we have this flexibility in scheduling. If you're on a telephone, right, real-time scheduling is more important, because if you can't be dropping, samples of what of talking or radio reception and all these different, very time-critical things that you need to schedule. Whereas if you're in a server room running a website, it's really about how many different processes can I run and how many users can I handle when they're hitting my website types of operations. So Linux is a very flexible operating system. Okay, symmetric multiprocessing. Okay, introduced in the second version or 2.0 version of Linux, of the Linux kernel. This is when they started supporting symmetric multiprocessing. Before that, again, we've seen that the problems that come up with single processor versus multiprocessor. Multiprocessor has a lot of different issues that we don't encounter in single processor. Okay. One of the biggest things that comes up is this idea that all of our kernel locking comes into question when we move to multiprocessor as opposed to single processor, right? We found that there are some problems that just can't be solved by simple turning off of interrupts and and running critical sections before turning them back on, right? We saw that with multiple processors, this will not prevent two pieces of conflicting code from running, okay? And that we need other locking mechanisms, like the main one that we've encountered is spin locks, okay? So they're showing here that what they do is use a spin lock to coordinate between the processors, and then this makes it so that only one of the processors can be running critical section code at a time. So inside the critical section of the one processor, that they can use traditional locking mechanisms like turning off interrupts, but then a spin lock that coordinates all of the different processors will make it so that only one of them is doing that at a time. Because what we saw before, does anybody remember why we needed spin locks to do critical section code? Why we couldn't just use turning off interrupts? I have two CPUs, CPU1, 0, CPU1, right? The idea of critical section means that that if I run critical section A and critical section B at the same time, there may be variables or some sort of information that they can clobber each other, and we see situations like in the producer-consumer where we get the wrong value in a variable at the end, depending on the sequence in which each of the critical sections ran. So the idea is that we can't let these critical sections run simultaneously, right? So the single processor way of doing that, right, is we'd have both of these critical sections running on one processor, but we'd be using scheduling to jump between them, right? To run a little bit of this process and then a little bit of the other process. Okay? So by disabling interrupts when we enter into critical section A, we make it so that we can run and we'll never get interrupted to run additional code, like interrupted to schedule critical section B while we're running that, because we disable interrupts, we get to the end, we enable interrupts, and then all the other things like scheduling and hardware interrupts can happen. Okay? But when we introduce another processor, what problem does that introduce? Right? Let's say I disable interrupts when I enter critical section A. Does that help me? Let's say I disable interrupts on both processors. When I enter into critical section A and critical section B. Am I still running two critical sections at the same time? Yes. So disabling interrupts, the only thing I help out with is that nothing on processor 0 can interrupt what's running on processor 0, and nothing on processor 1 can interrupt what's running on processor 1. But we still have two critical sections running at the same time. Okay? So, the idea here is that Linux uses a spin lock to determine which processor can disable interrupts and run a critical section. So the idea is this. If you think of a spin lock, right, as either pointing to the left or the right. Okay? So if the lock is pointing to the left, I get to this point and I say, I want to acquire the spin lock. Nobody's using it, so it says, okay, you can have the spin lock. Okay? So if I can acquire a spin lock, that means I don't have to wait. That means I can continue. So I enter my critical section, I disable interrupts, and I start running. Okay? Now, along comes processor 1 running, and it can run whatever it wants still, because it's a separate processor. It's not, just because a piece of code is running on processor 0, it doesn't affect processor 1. But when I get to a critical section, the first thing I'm going to do is try to acquire the spin lock. Can I acquire the spin lock? No, it's taken by processor 0, and it's running through its code. Okay? So if I can't acquire the spin lock, what do? I wait. And how do I wait? It's spinning, right? That's why it's a spin lock. So when I say, oh, I want to acquire this, I will spin until when? Until 0 basically unlocks the spin lock. So when I get down here, I'm done with my critical section. So first thing, it's safe to re-enable my interrupts. And the other thing is that I can unlock the spin lock. So I say down here, I say re-enable interrupts, unlock the spin lock. So the spin lock, right, will spin over, and this guy will be sitting there going through a loop going, can I have the lock? Can I have the lock? Can I have the lock? When it gets unlocked, I will be able to take the lock, I'll disable interrupts, run through, and continue on my way. Okay? So by adding in this mechanism, we made it so that all our kind of coordination of this and synchronization of all those different critical section problems, we can do it safely on these different processors, right? So that's just a simple way to make it so that we can kind of reharness all of the synchronization solutions that we used in a uniprocessor, in a single processor environment, we can now kind of adapt it to the multiprocessor environment. Okay. Memory management. Okay. We have all of the different types of memory management issues we saw in the more theoretical chapters. We have virtual memory. We have paging and all of these different tools available to us in memory management in Linux. Okay. Linux uses 3 different zones for the physical memory. Okay. They basically just break up the memory into zone DMA is for, everybody know what DMA stands for? DMA is direct memory access. Okay, it's a hardware this memory can be used for a hardware technique that really helps improve performance in that direct memory access. When we were talking about things like accessing a disk, right? We kind of threw out this idea of when I'm a process and I want to go get a piece of information from disk, I'll go ask for a piece of information from disk and I'll kind of waiting for the interrupt, right? And the benefit to that is that I can go take another process and run it, right? If this process that's waiting on disk information doesn't have any instructions to do, well, I might as well use the CPU for something else, right? One of the problems without DMA is the fact that if you're copying information from a disk or from a sound card or some other input device, right? One of the problems that comes up is, what if you need the processor to do that job? In other words, if I want to copy information off a disk, what if I need the processor to copy that information off the disk? Well, we get into a situation where even though that process is just waiting for I/O, we're tying up the CPU, getting that input-output done. Okay? So what happens is, as you get more advanced hardware, you can make it so that the hardware can do things like loading blocks of information from disk on its own. And how one of the mechanisms you can use in that is direct memory access, which means this disk controller or some hardware device that's getting the information has access directly to a piece of memory. Okay? That direct access to that piece of memory, that piece of hardware can write data to that area of memory without any intervention by the CPU, which means I could be reading information from the disk, because the whole goal of reading information from the disk is to get information from the disk into an area of memory. Why? So that the CPU can interact with that data, right? If I have, some numbers on disk, I can't do calculations on those numbers until they get into memory, until I load a copy of it into memory, and then I can run instructions on it, okay? So the idea with DMA is tell the disk, hey, get me this block of information. I'm going to give you a little area of memory where you can write that information. And then I'm going to go do something else while you do that. Okay? So the disk controller is smart enough that it can go find that piece of information requested, write it directly into memory without interrupting the CPU. Then, once we're done filling up the memory, or we've gotten all of that information that's necessary, then we send a single interrupt to the CPU to let it know this block is done. Okay? That really increases our performance in all of the ways that we kind of talked about theoretically with scheduling I/O versus CPU. Okay? So this area of memory is an area of memory that we have that capability. We can assign blocks of memory from that to these types of operations. We have the normal memory, and then high mem is just stuff beyond a limit that was typically accessible. A lot of the PC world had a lot of, there's a lot of difficulty once you get beyond an area of a particular limit of memory, where there was a lot of, I don't know, kind of duct taping and rigging of getting more memory beyond really 1 megabyte. Okay, when they were first developed, they were just developed saying, oh, we'll just make it about 1 meg of memory available. And then they didn't really think about going beyond that. And now here we are with gigs and gigs of, gigabytes of memory that we need to access. So there's been always a little bit of legacy of just dealing with smaller amounts of memory in most operating systems. Okay. And then also the various transitions going from 16-bit to 32-bit to 64-bit. All of these transitions change the kind of scale at which you look at memory, right? If you're a 16-bit operating system, you don't really have much, quite as much memory to worry about as, say, a 32-bit operating system, right? We've already seen that 32-bit operating systems are dealing with 4 gigs of memory, versus 16, which is not half the size; it's exponentially smaller. Okay. Just putting a memory in a buddy heap. Okay. This is to keep track of physical pages. Okay. We've seen that tracking pages of memory and frames that they're in, as we get to larger amounts of memory, okay, managing even the data that's managing the pages becomes difficult. So we break them up into different sizes. Okay, what is the relationship between the size of a page and the size of a page table and physical memory? So there's all these different factors. We have a page table. We have physical memory, right, frames. We have logical memory, right, a bunch of pages. And then we have a page table which maps pages to frames, right? So, physical memory, what determines physical memory? The size. Right, money, right? However much memory you buy for a machine and how much you can, that it's wired to be able to hold will determine how much physical memory you have. Logical memory? It's up to us. We can, it's up to the operating system. We can say how we want our memory to look in the operating system. Okay? So, what about page sizes? Also up to us. Okay? Both the logical size and the page size, that's also influenced by our hardware as well, right? Because, like, for example, we read a little bit about the Intel CPU, the Pentium CPU can handle, it has some kind of predefined sizes that it's good at dealing with, like 4K, 4 kilobyte size pages. If you do 4 kilobyte size pages, then you can use all this advanced hardware features, for managing some of the page information. But what is the relationship between these page sizes and things like the main memory, or the physical memory, the page table, and logical memory? I have bigger page size. What happens to everything in this? How does it affect physical memory? I have larger pages. I have larger frames, which means I have fewer frames, right, that can fit in the same amount of physical memory, right? If I increase the size of individual pages, they're all the same size, so I can fit fewer in a section of memory. Logical memory space? Same, right? If I increase the page size, this becomes smaller. What happens here in the page table? How many entries are in the page table? that can fit in logical memory. So logical memory size, or logical memory space size, divided by the page size will be how many pages we have, which means that's how big the page table is. So if I increase the page size, my page table becomes smaller, right? Because I have fewer pages. Okay? So why don't I just have big pages to make my page size, my page tables very small and manageable? In what way? Okay, so every time I need to allocate any memory, I allocate a whole page, right? So that's fine if I can fill up an entire page. But any remainder after filling up some of a page, I can't use, right? So if I have very large pages, I will more often have remaining space that I can't use. There's actually a term for this. Anybody remember the term? Internal fragmentation. Okay? So, the idea is you want to get a balance between these page size. Why don't we make them all very small? All the pages. Well, if we make them small, this becomes, right, very big, and it becomes a problem even managing the page table to manage the pages going in the frames, right? What if this gets so big that we're using many, many pages to even store it? Well, now we're doing a lot of our page management just managing the page tables before we even get to running a program, okay? So there's a balance between these two. This buddy heap algorithm, okay, is a way of helping with managing this free number of pages, and not necessarily the page table, but at least managing what kind of memory is available. Because again, tracking how many free frames we have and what's allocated and what's not is all related to the page size, right? Smaller pages means more entries. Larger pages means fewer entries. So there's this relationship. So the idea behind this buddy heap algorithm, okay, is you consolidate as much as you can the amount of free areas, and as these free areas come next to each other, you can actually summarize them into a larger entry. So if I find myself with two 4 kilobyte frames free, and they're right next to each other, I can actually summarize them as a larger 8 kilobyte block, and so on. Make it so that as more memory gets free, I can have fewer and fewer entries, despite the fact that my pages are a fixed size. Okay? So, this is a technique that they use to kind of alleviate some of the problem of the types of information you have to track in order to manage all of your memory. Okay. Virtual memory. Okay. Two separate views of a process address space, right? We have a logical view, which is the same as what we've been seeing in all memory. Just one big continuous page-aligned block. Okay, this is the same thing that we see where we say you have this much memory, all divided into equal-sized pages. Okay, but then we have a physical view of each address, which is stored in the hardware page tables. Okay, this physical view is not only the idea of what pages are stored in what frame, but also the idea that some of these pages reside nowhere in memory. They're on disk. Okay, so there are points where this idea of page faulting, where we go to get a particular page and it's not even available in memory. We need to load it into memory and then show what the mapping is into physical memory. Okay. Actually, before I move on, Does everybody understand the two different types of problems that occur when you try to access a logical address? I'm in the program, there's a logical address space where I need to get to a particular memory location. There's two problems, okay? One is the fact that I need to translate this into a physical address, right? In other words, I need to find the frame where that page is stored in order to get a physical address so that I can perform an operation on that location, okay? There's a second problem when you involve virtual memory. The second problem with virtual memory is I don't map to any physical frame because I'm not loaded, right? So I need to go to somewhere else, load that into a frame, and then still have the original problem of mapping the logical address to the physical frame. So do you see how there's those two problems where the virtual memory problem of finding the page, you also still need to do the original problem, which was mapping a logical address to a physical address, okay? What they're talking about here is the physical view in that second scenario of it's not even in memory. I need to load it off of disk or some other mechanism, load it into memory, and then I just need to go ahead through the regular memory mapping that I had before. Okay? Virtual memory regions characterized by the backing store and the region's reaction to writes. Okay? The backing store. This is fairly simple. The backing store is just where is this stuff stored when I don't find it in memory. Okay, this is usually going to be a swap file, or in Linux oftentimes a swap partition, where you have a whole section of your disk just allocated to swap, in other words, virtual memory. Okay? The region's reactions to writes, page sharing or copy on write. What is that? What is copy on write? And where would it come up? When? Okay, before it's written. As opposed, so when would something like this come up? Wait, what?
When you open the file from right there, but there's another one you have to read the file. So
Okay, well, there may or may not be a file involved, but the idea is, yeah, is like that. If, set up the scenario. Okay, I have two programs. Okay, when does copy on write really? When does it? Two programs. I load two programs completely unrelated to each other. They load data up and they write the data and they calculate on the data. Do they have any copy on write issues? Would copy on write be used? I load my word processor over here, my web browser over here, and they run. Do they have copy on write issues? No. What kinds of things have copy on write issues? What's that? Not threading, but close. Forking is one of the main places this happens, right? With fork. What is fork? So you take one process and you create a new process. What's unique about fork? What's the difference between fork and thread? Which ones? Which ones do they all have their own memory? Forking does, right? Whereas threading shares the same memory. Okay? But even though both processes in a fork have their own memory, how does that memory start off? A copy of the other memory. So I have process 0, I fork and create process 1. Well, initially we both have the same view of memory, right? So, what's the efficient way to make a copy of all that memory? Do you copy all the memory? Do I take each page and make another copy of that page in a frame? No. What do I do? Right, so first of all, what I do is I don't copy all the pages. I just point both programs to the same set of pages. Okay? The problem occurs when if one of the processes write to a location in memory, how should the other process see that location in memory? If I have a variable that I change in process 0, what happens to that variable in process 1? It doesn't see the change, right? So can I use the same area of memory to point to that variable? No. So what I do is I copy on write. When I'm about to write, I stop the write. I make a unique separate copy of that page and write to it. That way, the original process, or the original page, can have the old value because it doesn't see the change. Okay. Right before I change a variable, right, I call a fork. So both of them have the same view. They have their own copy of the same values in memory. When one of the processes wants to change, say, a variable, I don't let it change the variable in the shared page of memory. I create a copy of that page for that process. It can change the variable. The original variable is untouched, so the other process doesn't see the change. And they both continue running. And anytime either of them is about to write to a particular memory location, right, we create a copy of it. Okay? So we only make copies of pages that need a copy because they need different views of them. But for all of the pages that we don't change, we saved ourselves all of the time of copying. So what they're saying here is that all that kind of behavior and whether or not this process needs to exhibit that behavior is all stored in these, is tracked by Linux in its virtual memory system. Do you see how this idea of making these copies of memory by just pointing both processes to the same memory, do you see how this is a form of virtual memory? It's making it look like you have more memory than you actually have. Because technically, if I do fork, each of these should have their own copy of the memory, right? Well, we're making one block of memory look like twice that size. Okay? And so we create these new virtual address spaces through our different mechanisms that we learned about before. Fork, and exec is running a program in place of the program you're running. So the idea is you typically fork a child process and then exec some new code there so you're not running the same code as the parent. Let's see what else we got here. Okay, two sections of the virtual memory paging system, the virtual memory manager, right? Okay, we have a page out policy algorithm, okay, and then the paging mechanism that actually does the copying of the shuffling of these physical pieces of memory from disk or back in the store to frames and so on. Okay. What does this algorithm decide? This page out policy algorithm. We have virtual memory. The general idea is I go to access a particular page. That page is not available. I need to go to disk and I need to load it into physical memory. Okay? what part of that does the page out algorithm need to answer, or solve? Right? Any algorithm that we have is a decision, right? It's some sort of, you ask the algorithm, like it's, like an oracle, you say, hey, what should I do next? And it should do some calculations and say you should do this next. So what answer do we get from the page out algorithm in all of that virtual memory mechanism? It's that's one thing that it needs to answer, is what do I do when I alter a page? Because we have a problem now, it's different from what it looked like on disk. What else? Main memory. Yeah, we need to decide what to take out, right, and what to do when we take it out. Right? If we need a free frame, we need to do something with the page that's already in there, right? Because we need that frame so that we can load something else in. We don't have a problem with deciding which page to load in. We're loading it in because we need it, right? We have a problem with which page do I need to take out and what do I need to do before I take it out? Because if it was altered and its version on disk is different, we can't just throw it away, right? We need to store it and all that kind of thing. Okay, so that's the kind of decisions that that the virtual memory manager needs to make. Okay, let me see. This we can talk about very briefly. These are program formats. When you get down to the very detailed aspects of programs on a system, it's real easy for us to say that you go in the shell, execute a program, and it loads it into memory and starts running it. Okay? But at the implementation level, you have to decide, well, what does a program look like on disk? How does it communicate to the operating system? What other libraries it needs to load? How it needs to set up the memory when you're loading it. There's a lot of questions that need to be answered when you execute that program at the command line, right? When you run a program, we obviously need to load some code from that file, right, because it's the program. But then there's also other things that happen, like loading in libraries that are shared and that kind of thing, okay? So Linux actually utilizes two different ways of storing those programs on disk. In other words, the types of information that's embedded in that file to make it so that you can run the program. Okay? There are two formats, elf and a.out. Okay? A.out is an older style. Most modern programs on Linux are not compiled for this a.out. Okay? Most of them are compiled for elf. Elf stands for I don't know. I don't remember what ELF stands for. It's something loadable format, I think, or loading format. But just generally, the idea is a header, right? A header is just some information embedded in that file, which has this header information which says what other types of things to load. And then from there, after the ELF header, you have the program in pages. So the idea is that you should be able to read the ELF header to learn about what other things need to be done when loading this program. And then you can start copying pages of that program into memory, just like we've been talking kind of with our little diagrams of pages loading into frames and whatnot. Okay? So ELF is just really a format for storing programs on disk. And it's a format that helps when running that program to tell the operating system how to load the pieces. Okay? And then this is just a layout of the program once it's loaded. Okay, once we load it, we have all these different pieces inside memory. We've been talking about these pieces of memory in the general sense of we have code, we have some data, we have heap, and then stack. But this is specifically how an ELF program looks in memory. Okay, so we're not going to spend too much time looking at that. Static and dynamic linking. Linux has all of these capabilities. We learned about many different styles of linking to libraries. We're not going to go back over them, but the general idea is that you have static linking where you actually copy a piece of library code into your program so that you can load it when you run it. And then there's the more advanced style of you run a program and instead of copying library routines into your program, you just load the same library for all programs that might use it, and you all just point to the same place. So on Windows, these are DLLs, right? Dynamic linking and loading, or dynamically linked library. Yeah. So DLLs are on Windows. We have shared object libraries on Linux. So it supports all of these mechanisms. File systems, we didn't really talk a whole lot about file systems in theory, but Linux actually supports a huge number of file systems. This ext2 FS is the standard one. These days they use ext3, which is a journaling file system. But we didn't really talk about file systems. There's a lot of different factors that determine kind of what your capabilities are. Let's see what else we got. That's about it. Just real quick on the security. Okay. Luckily, most of what we've talked about in terms of security, like permissions and things, we talked about in the context of Unix, and that kind of carries over. One mechanism that's kind of available in Linux as in Unix is this idea of set UID. The idea is that you can run programs in the context of another user. So even though my user might be Steven or whatever, some programs might be provided where they run as a different user, okay, that I'm still capable of running. So I can run it, and while that program's running, the operating system sees it as a different user. This creates some powerful methods of delegating permissions to users where this program can run as a different user, but you don't have to generally give me the same permissions as that user to execute things. Okay? Yeah, that's about it. Okay. This Thursday, we're going to talk about projects. Okay. So what I'd like everybody to do on Thursdays, send me I'll send out an assignment, but send me a brief, maybe half page to a page abstract of what you're planning on doing. The main thing is I just want to have kind of in a document just what area everybody's working in, so that I can probably send out emails and things with suggestions for those to kind of steer everybody away from each other's areas, so that we see a lot more of the kind of operating system world. So just send me just real briefly what area you're working in, whether it's memory or it's security or scheduling or just the general area. What aspect of that you're interested in. If you already have some ideas of what kind of experiment you're going to run or research you're going to do, go ahead and put that in there as well. But it'll just be a brief half page to a page. Think of it like an abstract for what you're going to be doing. And I'll send out an assignment for that. And then next week I'm going to really just cover the projects, discussion of what you're specifically doing, and then some talking about kind of what I'm expecting in the paper and how the paper should look, and some suggestions for doing experiments, collecting data, graphing, and stuff like that. Okay? So That's it.